Back, problem 3 of section 3.8 on our web work course. Notice this is the last problem on section 3.8. The purpose of this question is to tell you that Newton's method is not always workable. That is, it doesn't always give you a good solution. Newton's method will converge to a true solution if you have a good initial approximation. So you do need a good initial approximation. If you don't, then it may not converge at all. Okay, so here is an example where we will see that our initial approximation is such that you don't converge to a good solution. So consider the example of the polynomial x cubed minus 3 equals 0. Okay, so polynomial equation. Now this factors here. Look, x is common. What is left is x squared minus 1, which splits as difference of squares. So you know by hand you can solve for this. This equals 0 gives you x equals 0, x equals 1, and x equals negative 1. So negative 1, 0, 1 are the three solutions. We can find it by hand. We don't even have to approximate anything. Okay, but suppose we want to approximate. Okay, just to show why Newton's method could fail even in an easy problem like this. So that is my function x cubed minus x. When I take its derivative, I get 3x squared minus 1. Okay. Now, when the derivative is 0, see what happens. When the derivative is 0, I get 3x to the power 2 minus 1 is 0. That means 3x to the power 2 equals plus 1. That means x to the power 2 is the fraction 1 over 3. In other words, x equals plus or minus square root of the fraction 1/3. Okay, which is same as plus or minus 1 over root 3. Okay, why is this important? Look at the Newton-Raphson method. Denominator is a derivative. So if I had this number, in either of these numbers, plus 1 over root 3 or minus 1 over root 3, as my initial approximation, I already fail. I cannot proceed because that makes the denominator 0. Derivative 0, denominator. So I cannot proceed. So let's choose something other than these two. Okay. Now, they are suggesting try square root 5 over 5. Okay, try that as your initial approximation and use that to find x1. Then use x1 to find x2. Use x2 to find x3. Use x3 to find x4. All right, so let's try. First, let's figure out what is x0. We can plug it in here by saying square root of 5 over 5. That is what this is, right? So let's plug it in and see what you get. Aha, we get a certain number and they say it's correct. Of course it's correct. All right, now use that x0 to find x1. Remember, what is Newton-Raphson method? Use an old approximation to get a new approximation. Okay, so let me go to our picture here. So the idea is the new approximate, the new approximation is obtained using old approximation minus f of the old over derivative of the old. This is the formula, Newton-Raphson method. All right, so this is my old approximation. I'm going to build x1. So how do I get x1? I have to write x0 first. So let me write x naught first. Okay. Let's make sure we can see both the pages. Okay. X naught first. All right. That is x naught. Then I want to say minus f of x naught. F of x naught. So I need to take this number power 3 minus the same number. So I'll take, by the way, this is a quotient, right? So I will write, while I'm typing, I'll make a quotient, something over something. Write things in parentheses, okay? The numerator is f at the old one. So my number, whatever I input, I'll put it in parentheses. So that's my number, square root 5 over 5, power 3 minus, write parentheses before you enter your number, square root 5 over 5. So that took care of the numerator. Now denominator, you understand? Denominator starts after the slash. So that's the denominator. What goes in the denominator? Derivative. 3x to the power 2. So 3 times parenthesis, that gets me my old x, right, to the power 2 minus 1. Okay, so I think I'm done. That's the denominator. Submit. Aha, that's correct also. Now look at that. That is the same as that, except for the sign. Okay, this is the same as this except for the sign. Okay, so which is easy. To find this, what I'll do is I'll use my same expression, cut and paste here, but wherever I see square root 5 over 5, I will put a negative of it. Do you understand why? I put a negative because it's essentially the same value except for the negative. So wherever I see square root, I'm putting it in a negative in there. A negative before the square root, before the S, letter S, to make sure I don't make any mistakes. So 3x squared minus 2, so I'm done. Submit it. Aha, that's correct. What do I get? Look, I get the same number as my original number. Okay, in other words, how do I get the next one? Look, that was minus, this is positive. So now I will take the same expression as before. Instead of the negative, I should make it positive. But didn't I do that? That's what I did here. Okay, so it's same as doing this. Submit. Aha, that's correct. Now I have a negative. So I will cut and paste the one negative version. There you go. They are all correct. So what went wrong here? See, I'm not converging. I'm going positive, negative, positive, negative, positive, negative. That is, I'm oscillating. So what's going on here is best explained with a picture. Okay. This picture may not be very clear. Let's draw another picture. Let's draw our function x cube minus x to the power 3 minus x. That was the function. Okay, minus x rather, I'm sorry. All right, so let's zoom in. What's happening? Okay, this is a cube. Look, somewhere you have horizontal tangent, and those were the numbers plus or minus 1 over root 3. So somewhere here you have a horizontal tangent. Okay, both the positive and the negative. What about, so that's this number, okay? What about this number? That, if you see the value of it on your calculator, you will get something less than 0.5. Let's check, okay? So, what is it? Square root 5 over 5. It is 0.447. Didn't we just see it? That was 0.4472, blah, blah, blah. So that number is smaller than 0.5. So it's somewhere here, okay? Here. When I take its point on the curve, its tangent hits my curve again there. When I take the same tangent, gives me here. In other words, this point gives me approximation here, this point gets me approximation here. So I'm just getting pushed from here to here, here to here, here to here. I'm never approaching any number. All right. So that is why Newton's method may fail. Okay. Because my initial number was such that my approximations kept oscillating between the two numbers. Okay. So Newton-Raphson's method, while a very powerful method, it has its limitations. All right. So this completes section 3.8 with me. Next set of videos will be on section 3.9. Until then, bye.